Okay, so what you can see in this experiment is we have a drive motor here that drives this drive inertia, and we go through a belt which is simulating a gear system to this load inertia. So the drive runs in this direction. Both of these inertias have shaft encoders on them, so we can take the feedback from these two encoders, go back through the computer and implement control algorithms on this drive motor. So here you can see the model of our feedback loop. The mechanical plant model is here, and here I have my PID controller, and I can set in proportional, derivative and integral gains to whatever values I choose, and so implement any PID controller I want to. Okay, so first of all we're going to start with a simple proportional gain for the controller, and we're going to execute a closed loop step. Okay, so the commanded response is shown here in red, this step, and the actual response is shown here in green, and you can see that the response is kind of sluggish, and we have a big steady state offset and a little bit of overshoot creeping in, but certainly it's too slow and it has too big an error to be acceptable. So now we'll run this higher gain controller, and that speeded things up, but as you can see it puts a lot of oscillation into the response, and I'm pretty close to going unstable. So now you see with the larger proportional gain, I am getting better steady state tracking, but I've got way too much oscillation in this response. Okay, so what I've done now is I've added a little bit of a derivative term. So now I have a PD, proportional plus derivative controller, and the fact that I allow feedback at the derivative gives me a bit of anticipation and should let me run with a much better transient response. Okay, so now you can see that the response of this PD controller is much improved. I get a much faster response and pretty good steady state tracking, although I still have a little bit of steady state error that I'd like to get rid of. So now I've added a little bit of integral action, so I have a true PID controller, proportional integral derivative, and what we'll see is a very similar transient response, but now the integral action will take out that little bit of steady state error. So there you see the integral response creeping you to steady state, and there again. So now you can see with the PID controller I get that same nice fast response with a minimal little bit of overshoot, but here you can see how the integral part of the controller gradually works on that error and takes it all the way down to zero.